Be giving you some notes on section 4.6, which is the mean value theorem. And I told you guys that, well, back when we first started the course, I said if the theorem has a name in our book, that's a good sign that it's an important theorem, okay? This may be the most important theorem in Calc 1. It's going to get used again and again and again in a lot of situations, okay? Really to prove other results is what it's for. But you have it in front of you on the worksheet, and I thought before we do anything else, let's talk about what it says, okay? And how it applies to an example. Because I feel like when you want to learn mathematics, you have to do examples, okay? So here I have well, a function, 2x over x squared plus 1. Did anyone sketch the graph of that function yet? All right, well, I'm going to do that now then. And it says that there's a value of c guaranteed to exist on the open interval. And the open interval I'm talking about is this -2, 2. So I'm going to go ahead and use the graphing calculator. Let me type in the function. So if I go to the y equals screen, I'll type 2x divided by, and I better use parentheses for the denominator, we have x squared plus 1. Okay? And when I hit zoom, I guess I could use the standard window, but because I'm just going from -2 to 2, I can go ahead and zoom in and get a really nice look at what's going on here. Okay, so there's my function. Right? And from -2 to 2, we're talking about from here. So for example, maybe I'll evaluate the value right at -2. And it says it's -0.8. Right? And actually, you could probably compute that. If I'm going to sketch my own graph here. Okay? So if I computed f of -2, that would be -4 over, well, 4 plus 1. Yeah, -4/5 is -0.8, right? So here's -1, here's -2. The output is not quite to -1. It's about right there. What about positive? What if I evaluate f of 2? What would that be? 4/5, right? Because the only thing that changes is that negative sign won't be there. So that's why you have some really nice symmetry here. What kind of symmetry do we have, by the way? It's an odd function, right? How do we check that? So it's symmetric with respect to the origin. And just looking at my picture, right? My picture looks something like this, and then it comes down and goes through 0, 0. And it looks symmetric with the origin, respect to the origin. Of course, if you plug in f of -x, well, that would be this. And you get -2x. This is the same as x squared plus 1, right? So you do get negative f of x. So those of you that said it was odd, I just proved it now, right? It looked symmetric with respect to the y-axis, but now I proved it. Okay, so now this mean value theorem says, and the symbol here next to the C, the backwards E, what's that mean? No.
There exists.
There exists. The for every was the upside down A, okay? So I just want to make sure you're clear on what this is. The mean value theorem is an example of what is called an existence theorem. It says that something exists. We've seen other existence theorems in this class. Do you remember the names of any of them? The intermediate value theorem was one. There was another one called, now the squeeze theorem was a theorem we covered, but that was not an existence theorem. That one just said the limit's going to be the same as the other two limits. There was another one called the extreme value theorem. Okay? And that one we just talked about in the last chapter. It had to do with when does a maximum occur? Okay, and I'll be talking about that in a little bit, so I just want to bring that up. But existence theorems just tell you something exists. It doesn't tell you how to find. In this case, what is it that exists? Some number C. In our example, we're gonna find a number between, well, it says A and B. There exists a C on AB. So we're going to find a number between -2 and 2 such that what happens? F prime of C equals this big thing. By the way, this big fraction on the right, do you recognize it? We did. Do you guys know what it is? It's a slope. Slope of what?
Secant line.
Which line? Yeah, which secant line? I mean, you're exactly right. This is the slope of the secant line from where to where? Yeah, I mean, from the point AF of A, which is this point we just found, to BF of B. So I think it would go right through the origin. I think that would be the slope we're looking at, right? Does that make sense to you guys? So that's something I could compute. Well, my green doesn't show up very well on the screen. That's too bad I picked green. That's supposed to look different than that, but it really doesn't to you guys. All right. Well, this line is what that fraction computes the slope of, right? So let's think about what the theorem says, and I can do orange because this does show up. When we say f prime of c, okay, so remember, this is the slope of a secant line, but what is the orange? What's f prime of c? This is the slope of what? The derivative. That's the slope of a tangent line. So I think maybe that'll help you. What does the mean value theorem say? It says if I have f continuous and f differentiable, then there exists a place where the slope of the tangent line will be equal to what? The slope of that secant line. Are you guys with me? The slope of the secant line, by the way, is it positive or negative? It's positive, right? As I go from left to right, I can see it's going up. Here's my first tangent line, just past A. Is that slope negative or positive? That's negative. If I keep going, stop me when I get to be a slope of 0. Okay? So now my slope's 0. But I'm still not the same. Stop me when I get to have the same slope as the slope of the secant line. Think so? There, somewhere around there, right? And then I would actually go past it, and then there actually would be another place where, again, you see that? So in my mind, I think there are two places where the tangent line would have the same slope as the secant line. What does the mean value theorem tell me? It tells me that at least one place that has to happen. That's what the mean value theorem says. It doesn't tell you how to find them at all. It just tells you it exists. And sometimes that's all I need, is to know it exists. Now, what's the homework exercise? Morning, Mike. Just grab a sheet. The homework says you can try to find C, right? So really, the homework, it's almost just an algebra exercise at this point. But I think it's a good exercise for understanding the theorem a little bit. So here we go. We'll see if you guys got this or not. So we need to find f of b minus f of a over b minus a. Okay? So the MVT, short for what? Mean value theorem, guarantees there exists a C such that, well, let's write that. F prime of C is equal to, and I guess over here I can fill in F of B, and that's up here, right? This was 2 comma 4/5. So F of B would be 4/5 minus, and what's F of A going to be? Negative 4/5. We computed that already. Over, and this would be, B minus A would be 2 minus negative 2. Right? Are you with me so far? So that's the equation that I basically want to figure out what C is. This equation right here. Oh, I skipped something. Something very important. I said the mean value theorem guarantees there exists a C. It only does if we satisfy the hypotheses of the theorem. See, these are what is needed. You need this. Do we have that? Let's see. Is f a continuous function on negative 2 to 2? Let's see. F of x is continuous. Is that true? I mean, it looks like it.
Yeah.
The only time that rational functions are not continuous is if the denominator equals what? Will this denominator ever equal 0? Then I'm okay. So f of x is continuous. Check. F of x is differentiable.
Yeah.
How do you know? Notice it only has to be differentiable on the open interval. It has to be continuous on the closed interval. I said, how do you know? Well, did anyone find the derivative? Well, let me do that then. Because if you can compute the derivative, then it's differentiable, right? So here I go. To show that it's differentiable, let me compute f prime of x equals what? Well, I guess it would be, quotient rule, right? Ho d hi. So here I go. X squared plus 1 times what? Yeah, but I need the derivative of 2x, so I'll just put 2 minus 2x times 2x all over ho-ho. Ho-ho would be x squared plus 1 squared. So I'm getting that f prime of x is equal to, I guess it would be 2x squared plus 2 minus 4x squared over this stuff, x squared plus 1 squared. So that's negative 2x squared plus 2 over x squared plus 1 squared. And now I'm starting to fall off the map, so I'll put this paper up a little bit. How's this look, okay? So I guess the only calculus I had was right here. I computed the derivative. Now, what does the mean value theorem says? It says there exists a C such that this is true. Well, that means put a C in for this expression. So let's see what I have. I have negative 2c squared plus 2 over, I guess it would be c squared plus 1 squared is equal to, now this would be 8/5 in the numerator divided by 4. Right? 2/5. So I've got stuff equals 2/5. You with me? Can you solve that equation? Yeah. The mean value theorem does not help you solve the equation, but I think I can. Let me try. I'll cross multiply. You guys good with that? That's how I solve a proportion. So let's see. I have 5 times this stuff. So let me write it as 10 for the 5 times 2 minus 10c squared for the 5 times that is equal to And then I have, wow, 8/5. No, I don't. Get rid of that. 2, good, times what? Well, this is c squared plus 2c plus 1. If I square a binomial, I get a trinomial. So I'll set this side equal to 0 and bring everything over to that side. So now 0 equals 12c squared, because 2 plus 10, plus 4c, and then what? Am I going too fast? 12c squared plus 4c. What about the constant term? What would I have? There's the plus 2. I'll subtract 10 since I have the 10 over here. You guys okay if I write minus 8? We found an error. Thank you, B. So when I square c squared plus 1, this is c to the 4th plus 2c squared plus 1. So let's try again. All right. Do I have enough room? I think so right here. Let's try again. So I have 2c to the 4th would be the highest degree term I have. Right? Now how many c squareds do we have? Well, let's see. 2 of them here times 2 is 4 plus 10 plus 14c squared. Yeah? And then I have plus 2 minus 10, so minus 8 equals 0. How's that look? Better? Okay, let's keep working. Factor out of 2. I'll just divide both sides by 2. And I get c to the 4th plus 7c squared minus 4 equals 0. Holy mackerel. How do I solve that? No, factoring only helps if it's set equal to 0. So I'm kind of...
It would be c squared times c squared plus 7.
Right.
Equals to 4.
Equals 4. Factoring out only helps if it's set equal to 0, not if it equals 4. So I'm going to leave it equal to 0. Okay? But what I'm going to do here, I'm going to use the quadratic formula. Do you see it as a quadratic in disguise? Do you understand what I'm saying? Or what some people would do is they would write like a substitution. U squared plus 7u minus 4 is 0. That's what I'm solving. Where my u is equal to what? U is the same as c squared. Does this make sense? It's not pretty, but it makes sense. Huh? Well, let's see. I better do a little work somewhere. Here. Let's do it here. So u squared plus 7u minus 4 is 0. U equals negative 7 plus or minus the square root of... Jeff, are you with me or you have a question?
No, I'm good now.
Okay. 4 times 1 times negative 4 all over 2. Ha! So this is negative 7 halves plus or minus the square root of, this is 49 plus 16 all over 2. So this is negative 7 halves plus or minus the square root of 65 over 2. Now, remember this is u, right? But what did u replace? U was a substitution for what? C squared. That's right. Now, if I write down c squared, we're trying to keep it real. So c squared has to be positive, right? So I claim the one I want is the plus, not the minus. If I put a minus, they're both negative, right? So c squared is going to be basically negative 3.5 plus, it's too bad it says square root of 65. Because what's the square root of 64? 8 divided by 2. 4 minus 3.5 would be just about a half, right? So I'm getting that the C values are going to be right around a quarter. C is going to be plus or minus the square root of this stuff. Negative 3.5 plus the square root of 65 over 2. Now, this is really kind of a cool calculation we just did. Remember a long time ago we computed f prime of C? But we also computed AROC. F prime of C is IROC. We computed AROC, the slope of the secant line. What was the slope of the secant line? It was 2/5 when we simplified, right? 0.4. Okay. What I just computed is that if I use either of these C values, IROC will also be 0.4. Let's check that on the calculator and make sure that that's true. So here we go. I'm going to hit second calculate. Have I shown you guys this one? Choice 6?
Yeah, but we didn't really work with it.
Okay, well let's work with it now. It computes what?
Derivative.
The derivative. But you have to give it which x value you want. See what I'm saying? Now the x value I want to try is my C value up there. And you could type it in and let the calculator do the work for you. So I'm going to hit square root of what? Negative 3.5 plus square root again of 65, close parentheses, divided by 2, and then close parentheses for the big square root. Enter. Look at that. It calculated that C value, and what did it say was dy dx? Just about 0.4, right? It's off by a few hundred thousandths. I think that's pretty cool.
That's the calculator.
Right. Right. It is the calculator's fault, not ours. That's a good point. Well, actually, why did it happen? Because the calculator doesn't really know what the square root of 65 is either. It rounds. And so that's kind of what's going on there. You guys follow? So your homework, if you get frustrated at all with the homework, I'm guessing it's going to be the algebra. The algebra is a little nasty at times. Okay? But let's make sure we understand the calculus. You know, go back to the theorem here. Why is this true? Why is it that this C has to exist? And that's what I want to get at now. And in order to prove the mean value theorem, it's helpful to prove almost like an easier special case, an easier theorem. And so we're going to do that. We're going to talk about what's called Rolle's theorem. And so I'm going to use this little presentation I've done a few times on the mean value theorem to help us along. Here's what Rolle's theorem says, and you might want to write it down. So Rolle's theorem well, I'll write it down here. Rolle's theorem, we're going to let f be continuous on the closed interval a, b. So we studied continuity a lot already. We know what it means to be continuous, do we? At a point, when you take the limit, that's the same as evaluating the function, right? And then we're going to let also f be what? This is the same as the mean value theorem, actually. Same hypotheses, right? We need f to be differentiable on the open interval a, b. Okay? Now, for Rolle's theorem, we need one other hypothesis. suppose also that f of A is equal to f of B. You guys, we didn't have that on our picture, right? Let me put our calculator back up. Let me look at that graph. Our f of A was negative something, and our f of B was positive up here. So Rolle's theorem won't work on this picture, okay? But if you have that, then there exists a C somewhere on the open interval AB such that f of B minus f of A over B minus A equals 0. This is known as Rolle's theorem. I don't know when Rolle proved this theorem. I'm not sure. I should look that up next time before I teach. Well, anyways. But I remember studying this in college. So we want to talk about why Rolle's theorem is true and what it means. So what I did is I always give myself some hints on the proof, kind of how it works. Oh yeah. What does the extreme value theorem tell us? This is actually something I mentioned earlier in class today. Now, when did we study the extreme value theorem? We studied it just last chapter after we covered differentiability. Okay? So the way the extreme value theorem worked, you had these two hypotheses. You needed f to be continuous and differentiable, and then it said there exists. Okay? So I can say this. By the, this is my proof of Rolle's theorem. By the extreme value theorem, actually, I don't even think you need differentiable. I think you just need continuous. We know that, so yeah, all I need here is continuous. So let me even say a little more. By the extreme value theorem, since f is continuous on the closed interval AB, we know it assumes both a maximum and a minimum on AB. So that's what the extreme value theorem says. You guys remember the theorem? How many think they remember the theorem now that I stated it? Oh, it's a good thing I'm reviewing. So the extreme value theorem says somewhere you're going to find a maximum, somewhere you're going to find a minimum. We covered it in section 4.1. Let me see if this helps you remember it. The next thing I'm going to ask you is, where will I find the maximum or the minimum? Either at the endpoints or the critical value, right? Now, you have to find a maximum and a minimum, right? Now, what if the maximum and minimum are at the endpoints? Wouldn't that be a boring function, though? Because if the endpoints are the maximum and minimum, right? Then how could that be unless it's just like a line, right? Or something like that. It could start growing, squiggle, and then continue to grow or something like that, yeah.
I forget the function. It just goes downwards and just levels out of one.
Yeah.
Like that would be an example of one of next.
Right. Like if you did 1 over x on some closed interval, you'd have a maximum here and a minimum here at the endpoints. That's right. So, okay. So we know that f is oh, but we can't do that. We can't do this because what was the third assumption that we didn't have for the mean value theorem? We know that f of a equals f of b. So wait a minute, this picture's no good. It's more like, here's f of a, here's f of b, right? So draw a function. Well, you're either going to go up or down somewhere, or you're going to have a really boring function. So either you have that, or you go up or down somewhere. So here's my next little hint of my proof, and I know what it says, but let's see if you can answer the question. If the maximum or minimum occurs at C, what is C? Maybe. Remember, C's a value on A, B, right?
We didn't have to have it from the client. Oh, wait, no, it's not closed.
You guys just told me something, actually. You told me, so the maximum or min occurs either at the endpoints, which I'm going to write down as boring, or at what? At a critical value. Yes. At a critical value. So what I'm saying is C is a critical value. Now, I'm underlining the word critical value because I want to recall, do you remember what it means to be a critical value? What's the definition? It's a value either where the derivative is equal to 0 or undefined or undefined. Oh, you guys, I screwed up the whole theorem. I can't believe it. Look at this. Do you see the difference? Look at the way I wrote it down. I wrote this. What's it supposed to say? There exists a C such that f prime of C is 0. No wonder. That's what it's supposed to say. It's supposed to be more like the mean value theorem. There exists a C such that f prime of C is that crazy fraction. Well, this one is, there exists a C such that f prime of C is 0. Sorry about that. Right. So critical values, we know that either f prime of C is 0 or f prime of C is what? Undefined. Yeah, it does not exist. Those are my two possibilities. But wait a minute. This is not possible because by assumption, what was the second assumption we made? F is differentiable. It kind of shows why you need differentiable. You got to make sure you don't have an undefined critical value. And so what this proves then is that, in fact, f prime of C equals 0, which is what I wanted to prove. Okay? So Rolle's theorem says somewhere, if you have f of C equal to 0, somewhere we're going to have, if you have f of A equals f of B, and you have continuous and differentiable, somewhere there's going to be a C such that f prime of C is 0. Okay? So here I go. To kind of walk you through an example or two. Take a look at this fun example. F of x is x to the 1/2 minus x to the 3/2. Okay? And so what is f prime of x here? Well, let's write it down. F of x is x to the 1/2 minus x to the 3/2 on 0, 1. So let's compute f prime of x. Oh, first of all, is this function continuous on 0, 1? Yay or nay? I'm seeing some nods. Yay. So what's the other thing I need to check? I need to check that f is differentiable on what? The open interval is 0, 1. Let's check that. How do I do it? Well, I take the derivative. Here we go. F prime of x is equal to 1/2 x to the negative 1/2, right? Minus 3/2 x to the 1/2. And it's funny because I've been writing those as with exponents, but you can also write them with square roots, right? How could I rewrite the function? This is 1 over 2 square root of x, right? This is f prime of x. Minus, and you could say this is 3 square root of x over 2 if you want, or something like that. Right? Is that okay? Question. Is this function differentiable on 0, 1? Oh, wait a minute. Here's the derivative. What's the only point you're not allowed to plug into that derivative? The only x value? Which one? Do you guys agree? You can't plug in 0. Or you'd have a 0 in the... Do you see that? But that's okay because you only have to be differentiable on the open interval. See what I'm saying? Not the closed interval. This one's okay. Yes, we are differentiable on the open interval. We are differentiable on the open interval. What's the other hypothesis we need? We need f of 0 to be the same as what? F of 1. Do we have that? Well, f of 0 is 0. What's f of 1? Well, it's 1 minus 1 is 0, right? You with me? So I can say we met all three hypotheses. So by Rolle's theorem, there exists a value c such that f prime of c equals 0. And I'm just going to look on my picture, and I'm going to point to where I think it is. Looks to me like if you solved it, it would be right around here, right? So a little bit less than a half is where you'd have the horizontal tangent line. Guys follow? That's Rolle's theorem, which we proved. One more example to look at is this one. F of x equals x minus 1/2. You have a cusp, yeah. Which means what? It is continuous. I could draw that with a single sweep of my pen, for instance. But it's not what? Where is this not differentiable? I can't either. Right in the middle there. You know, I can't see it either, but we can compute it. So let's do that. Let's try to compute the derivative. Here's one, okay, where I'm going to say Rolle's theorem does not apply here. I wanted to give you an example where the theorem doesn't work. Why not? Well, here's why. Because you go to compute the derivative, right? I can compute the derivative. That's not the problem. What would the derivative be? yeah, 1/3 x minus 1/2 to the negative 2/3.
Listen to the 2/3.
Oh, was it? Yeah, I think you're right. Yep. So this is 2/3. So this is 2/3. Oh, okay. So it's going to be to the negative 1/3. Thank you, Duncan. And then times 1. Bing, bing, bong. And so if I rewrite f prime of x, what does it equal? I guess it would be 2 over 3 times the cube root of x minus 1/2. Okay? So you guys, why is it that Rolle's theorem doesn't work for this problem? This is not differentiable where? At x equals 1/2. And the problem is, x equals 1/2 is smack in the middle of my interval. And that's why when you look at the graph, is there any place that the derivative equals 0? No. We do have f of 0 and f of 1 are both the same. They're both the cube root of 1/2. But yet there's no place that the derivative equals 0 on the picture. You see it?
Well, remembering what example it showed when you said how cubes were.
Yeah. For a cusp, you just don't know what the tangent line is. I mean, I would actually say the tangent line there is vertical, because it goes down, down, down until it kind of kisses, and then it has a vertical tangent line, which is undefined. So that's kind of interesting. All right, now we're ready for proving the mean value theorem. And the interesting thing is we're going to use Rolle's theorem. So let's do it. And my hint to myself is here on the screen. I'm going to apply Rolle's theorem to the difference of the function and the what? What's that say? Average rate of change secant line. So this is actually really kind of fun to prove for me. So here we go. I'm going to need a new sheet, I think. So I'm going to get a blank page, and we'll try and prove the mean value theorem. Here we go. This is actually good for us to just practice, okay? So here we go. MVT. Suppose F is, what's the first hypothesis? Continuous on closed interval AB. And suppose F is what? Differentiable. See, on the homework, you're going to have to check these hypotheses for the problems on the open interval AB. And I don't need anything about f of A equaling f of B anymore. Okay? MVT will say, then there exists a C in the open interval AB such that, what's true? F prime of C equals, and it's not 0 anymore. It's going to be, well, f of B minus f of A over B minus A. So I'm hoping that when you go home tonight, you get a problem that says apply the mean value theorem, you'll know at least what it says and kind of what it means. All right. So I said I'm going to apply Rolle's theorem to the difference of what? Of the function and the AROC secant line. Okay. So here's what I'm going to do. I'm going to start out by thinking about what the heck is the AROC secant line. Well, the AROC secant line looks kind of like this. Y minus y1 equals m times x minus x1, right? Now, any line looks like that. When I say the AROC secant line, on my picture from before, I'm talking about this green line right here. Okay? So I can fill in some things. I can fill in some things. So for example, I can fill in the slope. What's the slope of that line? The slope of that line was f of b minus f of a over what? B minus A. Yeah. And then I have x minus, and let me call this thing A for my x1. And if I do that, what do I have to call y1 then? F of A, yeah. Okay, so again, my hint to myself was apply Rolle's theorem to the difference of the function and the A-rock secant line. So one way to write the A-rock secant line is like this. Y equals stuff, f of b minus f of a, over b minus a times x minus a plus f of a. I just bring that f of a to the other side. That's the A-rock secant line right there. Okay. The idea of the proof of the mean value theorem. So, to prove the mean value theorem, we apply Rolle's theorem to what I'm going to call big F of x, which is equal to the original function, little f of x, minus y. Where, what do I mean by y? I mean this big mess. Okay? So let me write it out more carefully. Big F of x is equal to little f of x minus all this stuff. I better put it in parentheses. F of b minus f of a over b minus a times parentheses x minus a plus f of a. Okay. I want to apply Rolle's theorem to this. Can I do it? Well, I have to check my hypotheses. What's the first hypothesis of Rolle's theorem? The function has to be continuous. Okay, so let me check. Big F of x is continuous on the closed interval a, b. Do we believe that? Yes, because little f of x is, and so is my linear function y, right, this thing. And so I'm subtracting two continuous functions, right? And if you subtract continuous functions, the result is continuous. Check. Do you understand my argument there? Is that okay? All right, what's the next thing to check? Yes, big F of x is differentiable on the open interval a, b. Do we believe that? Well, if it is, we should be able to compute the derivative, right? Here, let's check that. What is big F prime of x? Well, it's little f prime of x, right? You do that part first. minus what? First of all, what do I know about f of a? That's a constant, right? Isn't almost all this stuff just constants? Where's the only thing that's not a constant? There's an x right there. A is a constant, right? The only thing I have to worry about is the x. So basically, I have a slope times x minus a plus another constant. When I take the derivative, you know what I get? The derivative of a line, isn't that just the slope of the line? So I just get f of b minus f of a over b minus a. Right? That's what big F prime of x is. And little f of x is differentiable on AB. That was the assumption, right? The only two assumptions I had was that f is continuous and f is differentiable. So check. Big F of x is differentiable. Now, again, I'm trying to apply Rolle's theorem to big F of x. There's one more hypothesis for Rolle's theorem that we don't have in the mean value theorem. Do you remember what it is? Yeah, so what is big F of A? Well, I guess I have to plug an A in here, right? So what would it equal? It would equal little f of A minus stuff in parentheses. But what does this stuff here all equal if you plug in an A? Isn't that a big zero there? Right? Why? Because I'm plugging an A in for the x. Are you with me? Plus f of A. Okay, guys, what's big F of A equal to? Which is? 0. Okay, so big F of A is 0. What about big F of B? I sure hope it equals 0. Let's see. I'm going to pause and let you guys try to compute big F of B. And if you can, then I think you understand the proof. So when I put it in here, I get little f of B minus, and then what happens here, the plus f of A I have to keep there. What happens here, this is maybe the interesting part, you have f of B minus f of A over B minus A, but then what are you multiplying by? B minus A. So what happens? B minus A is canceled. See that? So now f of B minus f of B, that's 0, plus f of A minus f of A, the whole thing equals 0. Okay? By Rolle's theorem, there exists a C such that big F prime of C is equal to 0. Now, what is big F prime of C? I guess I could fill that in right here. Big F prime of C, we know that that equals 0, right? But that would be little f prime of C equals, and this is, or minus f of B minus f of A over B minus A. So all this stuff equals 0. So if you want to prove the theorem now, just get this by itself. Move that fraction to the other side, and then you have what we were trying to prove. You see it? We got big F prime of C equals 0 using Rolle's theorem, and that proves the mean value theorem. So I think that's really kind of cool. So yeah, we're supposed to basically solve this equation. What did you guys get for g prime of x? 6x over x squared plus 3 squared. Okay. And then when you guys did g of 1 and g of negative 1, aren't they the same? Because this is an even function, right? So g prime of c, this part's 0. So the equation you're trying to solve is 6c over c squared plus 3 squared equals 0, right? And so what's your answer? C equals 0. And you can see that if you draw a graph. Here, the graph is x squared over x squared plus 3. Here, let me draw that because it's almost what I have here. Instead of 2x, I need x squared. And instead of x squared plus 1, I need x squared plus 3. But let me graph this one, right? Now, when I compute g of 1, that's right here, right? So my picture of this thing is like this. G of 1 is here. G of negative 1 is here. The secant line has a slope of 0, and here's where the tangent line has a slope of 0. Are you with me? All right. You can go on to number 3, or you could talk about homework. Either one. You still have a few minutes left. So yeah, we worked on this, but right away, is f of x continuous on 0, 2? No! Not at 1. Done. All right? So you can't even use the mean value theorem here. Hey, did anyone, some of you tried to solve it, right?
Yeah, I did. And it's like, wait a minute.
Wait, does it work? Hold on, let me look at the picture. I do have a minute. So what if I type in 2x divided by what? Is it x? Oh, it's x squared minus 1. Okay, so I'll put that x back in there. And then instead of the plus 3, I'll put minus 1. Let's see what the graph looks like. And we're looking at 0, 2. Oh, yeah. So you have asymptotes, right? So this is kind of funny. If you go from 0 to 2, that A rock would have a positive slope, right? But these are all negative slope, and these are all negative slope. You're never going to get a positive slope. Some of you may have been very frustrated if you went through the work to try and come up with the equation. So, anyways, nice work today, guys. Please, on Monday, I wanted to say something.